So today I will try to fit into the timings, and this is, do you hear me? Anyone? I mean,
Yes.
Yes.
yes, okay, thank you. So today I will try to make it 9:30 to 10:30 and then 9:50 to 11:50. If you have any questions regarding the previous lecture, please let me know. So just to remind you, in the previous lecture, we talked about k-means as a way of taking points in some discrete domain and finding and clustering them by first of all finding the center of each, the central representative of each group, and then splitting the domain to all points that are closest to this central point, and then shifting the central point according to whichever points belong to this specific group. And basically the representing points were competing with one another about who belongs to which region. And I told you that this is probably the most basic way of doing clustering. This is probably the most trivial one. And we also mentioned relation to an algorithm which is called Max-Lloyd or Lloyd-Max. Lloyd, you write like that, Lloyd-Max. Which basically deals with the continuous domain. So you have a probabilistic domain where you have some smooth function, and then so there is some, these are the level sets of this function, for example, the equal height control of this function. And then what you're trying to do is find representative points so that they would split the domain in a way that would that the weighted distance to each and every point would be as minimal as possible. And the question is, what is the relation between them? And in fact, you can show that if you have your distribution function defined at points where there are delta functions at these points, then these two are aligning. I mean, these two methods, I mean, these two ideas, I mean, the problems themselves align. K-means has probably an analytic solution only for the one-dimensional case. There is a quadratic, not quadratic side, not even linear programming. So there is a solution for the 1D case, but it's not really important that you know about it. What you need to know is that the fundamental problem in many dimensions is difficult, and therefore what we do is find this algorithm that would converge to some local minimum. Okay, so there is a quadratic programming way of solving that. Okay. What we will do in this lecture. So in this lecture, what we will do is we'll start examining more interesting functions. For example, we'll look at the function phi of t, where t belongs to some interval. Usually we'll call it delta or whatever. And this t gets values between phi low to phi high. Okay, so assume that this is my interval and these are my values. So therefore, this is where my function would live, and assume for a moment that this is a smooth function. And what I will have to do is quantize the temporal domain, I mean the x-axis usually uniformly, and then quantize the values that I assign. I mean, assume that I have only a specific number of bits, and we will somehow have to compete between how many bits we are allowing to the t, to the x-axis, and to the values axis. Okay, so this is the classical way of doing quantization in values as well as in time. And the answer that we will try to, the problem that we will try to address in this lecture would be exactly that. I suppose that we will finish this this chapter quite early, and thereby we will be able to continue to some more interesting problems. So let's define the problem. Assume that I have my function phi that maps 0 and 1, as we said before. So this would be 0 and this would be 1, and this is t. And phi is a mapping between 0 and t to some values. So these are the values of phi. And obviously they do not belong to a complex domain, but rather to the real numbers. And the first thing that we will do is quantize the t-axis uniformly. Okay, so assume that I have n such interval, capital N. So this would be 1, this would be 2, etc., and this would be interval number n. and we will denote each and every interval like that as delta of I. So we will have delta 1, delta 2 until delta n. Okay, and we have n such intervals. We will also say that the time representing each and every interval is called I mean t1, t2, etc., and the time would be at the center of each interval. So this would be, for example, ti. I hope it's not too small. So now the question is, so I have my intervals, and my intervals go from L equals 0. So it would be just phi L until phi L capital, sorry, now, okay, so this is quantization of the x-axis. Now we are about to quantize the y-axis. In the very similar manner, rather than quantizing it into n interval, we will quantize the phi axis into k intervals, and here it would be small k. Okay, so we have capital N for time and we have small k for values, and each and every interval would be defined. So this is the interval in the y-axis, and this is how it is defined. I mean, it would be defined from L-1 to L, and we multiplied the whole interval divided by the number of levels that we have, and this is how we define from where we start until where we end. Okay, so this would be, so this interval would be gamma 1, this would be gamma 2, this would be gamma 3, etc., 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 until gamma k. Okay, so L belongs to 1 to k. These are the so this is the game that we will be playing in this lecture. And now the question that we would like to answer is how to distribute my bits, my way of distributing knowledge into the x-axis and the y-axis. So assume that somebody is giving me large B number of bits. So somebody, some oracle is giving me, I mean, my job, my boss in I don't know, in Apple is giving me B number of bits that I can distribute between the time and the values. And now I have to do, to make this distribution in the most efficient way. What do I mean in the most efficient way? In the best way that would minimize the penalty of representing the signal, for example, using MSE, mean squared error. Okay, so this would be, so let's do it one step at a time. For each and every time slot, so let's zoom in into interval number ti. Okay, and this is how the function moves slowly from. So this would be ti, and this would be the lower part of this interval, and this would be the upper part of this interval, and this is how the phi function is moving along. What would be the most efficient way? Now assume that I can use only a single number to represent this smooth function. What would be my best choice using MSE? You should know by now. So somebody? I have to replace this smooth function with a single number.
The average.
Sorry?
The average.
Average.
Average. So Mark, or was it, yeah, or Omer, were saying the average. So yes, so if I'm just looking at the average, so for some reason it keeps deleting this. So if I'm looking at the average of these numbers, the average would give me the best MSE. And this is something that you should, by now you should be singing, okay? So the average should give me the best MSE, assuming that I can choose any number for each interval. So for the first interval, I will use this number. For the second interval, I will use that number, etc., etc. But I told you that that I also have to somehow quantize these numbers. I cannot just use any number. So for the time being, let's assume that I'm taking this y-axis, this axis of values, and I'm using a uniform quantization, which means that I equally space the sampling of this interval. Okay, so this is how I begin my my journey. And now the question is, is the following. So first of all, let's ask the following question. How many possible vectors, so assume that I quantized my x-axis and I quantized, assume uniformly my y-axis, and here I have k intervals and here I have capital N interval. How many different vectors do I actually have? So in the first entry, I have k possible values to choose from. In the second one, I have k possible values to choose from, etc., etc. In total, what I have is k times k times k times k times k possibilities, which means k to the power of n different vectors I can look at by quantizing the y-axis into k bins and the x-axis into n bins. Okay. Now, if I have these kind of many vectors, how many bits do I need in order to represent a given number? The number of bits that I need would be log 2 the number. Okay, any number can be represented by log 2 by LG. I mean, log of 2 is the shorthand notation is LG. This is why we say lelagleg for all those that are working in complexity. So we need log 2 the number of bits, or if we use the rules of the logarithm, we can actually take this n and move it outside of the outside of the power of the logarithm. Okay, so this is the number of bits that I will need in order to represent this all the possible vectors when uniformly quantizing the values and uniformly quantizing the time. Okay, so assuming that I'm using a uniform quantization to represent my function, what would be my MSE? Okay, so this is again uniformly sampling the time, uniformly sampling the x-axis. In a while we'll allow ourselves some more freedom, but this is the name of the game right now. So let's see what the MSE looks like. So the MSE would be summing over each and every time interval the integration. So let me zoom in into what is going on for time interval delta I. Okay, so in this interval, what I'm doing is taking the value of phi in this domain and replacing it with the quantization level that I've used before. So it would be some value probably in between. And if I open the parentheses, what I'm getting is the uniform quantization of y at point ti. Okay, so I'm sampling the value at this point. Okay, because this is the value that I'm sampling my signal with, and I'm just integrating over the values of my smooth function. Okay, so again, the name of the game goes like that. For the time being, the only thing that I'm looking at is sampling my function at these points. Okay, and then after sampling the function at these points, I'm uniformly quantizing the values according to what is going on here. Okay, so if, for example, n is really, really large, I mean, if I quantize my time interval in a really, really narrow intervals, so what I can do is, and also if I assume that my function is smooth, this is a reasonable assumption if I don't have anything else to assume, and then what I can do is just look at how the Taylor expansion about t looks like, about ti. So again, this is my time interval. This is my function here at this point. And what I'm looking is at the Taylor expansion of, and this is delta I. And what I will be looking is at the Taylor expansion of phi of ti. And I have the value at ti plus the slope that multiplies t minus ti. Okay, so it would multiply the slope plus second order I mean, higher order terms that I do not care now because I would like to have some reasonable estimation of my signal. Now, if I integrate, remember that what I have here is this integration of phi about this point, then what happens is that I'm integrating, so all the constants are being pushed out of the integral, out of the integration. And what I have here is integration over t minus ti, where remember ti is the middle of my interval. So what would be the integration in this interval over this line? Anyone has any idea? So this is my, now I'm basically integrating over this line.
It will be 0 because the two areas balance out on the left, on the right, I think.
Very nice, thank you. So this is Yagel?
Yeah.
Yagel, what we'll do from now is give one bonus point to every answer that would push the lecture forward. So please write a short note to myself and to Thomas saying that you gave a 1 point answer during the lecture. So what Yagel was saying is that since we have a straight line where the zero set of this line is 0, and I'm summing the area in a symmetric way, then this area would cancel that area, and therefore this integral will be equal to 0. Okay, and what I'm left is approximating the value, the integration over the value of phi in this interval is nothing but taking the central point times the interval. Okay, so this is in a sense this is something which is known. It's approximating the signal with a piecewise constant interval, and this is what we will use as first order approximation of our data. So let's see what is going on when we uniformly quantized our values of phi at point t. So again, now I'm getting, so this is my function. It used to be a smooth function, and now I sample it. I give these samples of these functions at equally distant points. And now what I'm doing is looking at these numbers and uniformly quantizing these numbers. So I'm taking this quantization of the integral time the integral itself. I can replace the integral by, as we showed before, by the Taylor expansion of this function about this point, and the quantization is left as follows. So now I can go into the MSE and plug in, instead of this term, that term. And what I end up with at the end of the day is something that looks like that here at the bottom. So all constants are getting out. I can do the integration because the integration is something because if I assume that there is a constant that is approximating my numbers, I can push it out of the integral. And at the end of the day, this is what I would be getting. Okay, here. And here is the error of quantizing. I still didn't deal with that, of quantizing the values of phi of t. Let's continue. So again, what I'm trying to estimate is the MSE error. And remember, somebody is giving me some number of bits, and I'm trying to distribute these bits into n that would display how many intervals I have in time, and k that would display how many intervals I have in the values. Okay, next. If I look now here at, we call this one the first term and this one the second term. So let's zoom in on just the first term. Okay, so what we'll do is push in the lower and upper values of this term, and let's just analyze the first term. So the first term would look like that. Okay, why? Because the size of each and every delta I is equals to 1 over n. Okay, and when we do the math, what happens is that this is what I would be getting. It would be 1 over 12. 1 over 12 goes from the power of 3 that I'm getting here. That in the integration becomes 1 over 3, etc. etc., etc. And at the end of the day, this is what we would be getting. Okay. Now, what we have here is summation over some values, and these values multiplies something that looks like dt. Okay. So if I go back from the discretization into the continuum, what we see is that we have some factor that multiplies integration over the square derivative of the function. Okay, so the first term basically measures the amount of energy of the derivative of the signal. Remember that we call it Dirichlet energy. The name Dirichlet is not that important. I mean, those of you who are afraid of crazy names, then please don't. But this is what the first term is telling us. It is telling us that that sum over the derivative of the function, and this is what we would be getting. And again, this is where n goes to be a relatively large number. Now, the second term is the quantization term. Okay, the second term is what happens when I quantize my phi values. Okay, the second term looks like that. It is basically summation over phi t minus the quantization of these phi's. Okay, so if we define the error of quantizing as follows, ti minus the quantization of phi ti, then basically what we sum is over the quantization errors. So this would be the quantization error, and that would be a measure of how smooth, in a sense, my function is. And this would be the total error, MSE error, when quantizing along the x and the y. Where does it lead us? Okay.
Can I ask a question?
Of course.
Where did the delta I go in the last equation? In the second term?
The second term or the first term?
The second term.
The second term. So let's go to the second term. Oh, remember that what we have here is, let me just do it like that.
Oh, because it's
remember,
1 divided by n?
Delta I, yeah, is nothing but 1 over n.
Okay,
So
thank
this
you.
is where it went. Okay, this is my delta I, basically. Why? Because we uniformly sample the x-axis, the time axis. Okay, and obviously I'm summing over the value quantization error through all the values of n. So this is why I sum over all the values of n. Okay, so now let's assume that somebody is giving me some knowledge about the signal. So it's not an arbitrary signal, and obviously not a specific one, because for a specific one I know how to distribute my values. But somebody is giving me some probability of the phi function to have value psi at each and every point x. Okay, and now what I will do is go. So again. Assume that I'm looking just at the phi values, and I'm telling you that the probability of getting, let's plot my function. So my function will probably look like that. So the probability of getting a value at these bins is much higher than the probability of getting a value at this region, okay? And somebody is giving me this probability. Somebody is giving me this probability as p phi of v, okay? So the probability of getting a value v would be p psi of v. So if somebody is giving me this probability, how do I plug it into the MSE? What I will do in this case is not plug it into the MSE, but rather weigh it in a way that measures the expectation here, okay? That we have already seen through the working with the averages has the same flavor. It is the same idea in a sense. So what we would be doing is subtracting v, the value at a specific point, minus the quantization of v, times the probability of getting v. And now let's work it out. So the quantization value, the uniform quantization value at v, let's call it phi L, because this is the phi and interval L, that multiplies phi and multiplies the probability, and this is the value, and we can actually split it into the k interval of phi. So remember, we have k interval of phi, and within each interval, what we do is we ask what would be the phi value that would represent my number. And assuming that I know what would be my phi value, all I need to do is, and I know that it is uniformly quantized, so it will probably be one in the middle. So what I know is that I need to subtract to sum over all these intervals. Now, since all these operations here are linear, I can switch the order of the integration and the summation. And since the probability does not depend on the interval I'm working with, I can push it out of the, but rather the, sorry, I'm taking it back. If I assume that the probability is a smooth function, then I can approximate the probability within each and every interval by the average of the probability in the interval, or by the value at the center of the interval, exactly what we did before with the Taylor expansion, okay? So I can push this probability out of the integration, and therefore I have here an approximation sign. And this would multiply the energy of subtracting V inside the interval minus the value of this interval. So again, this is when I have my quantization level really dense. I can actually use this approximation in order to do the math. Now, after doing this approximation, everything is straightforward because I have a quadratic equation for V, and this is something that we know how to integrate. Immediately, we get what is written here, and this should hold for each and every interval. And plugging these bounds into the integral, this is what I would be getting. So again, we assume that we uniformly quantized phi, and these are the values of this quantization level for each and every interval. Okay, so this is this value in the middle, at the center. So again, we didn't do much here, but rather quantize the probability, assuming that the probability can be assumed by a constant number within each interval. And at the end of the day, this is what we would be getting. So let's push it forward. So now the expectation of the square error. Okay, so this was the expectation of the square error. And now what we have is that we can put everything together and get at the end of the day that the expectation of the square error, given the probability, is nothing but phi high minus phi low, I mean the size of the interval, divided by the number of quantization level, k, squared, multiplied by 1/12, okay? So again, what we got at the end of the day is that the penalty of quantizing uniformly the phi values, the psi values, is nothing but the size of this interval. So it would be phi high minus phi low divided by k, and then you square it. And so this would be basically the squared size of each of these interval multiplied by 1/12. Okay, so this would approximate the quantization of representing the values by these quantized values, uniformly quantized values of the psi axis, sorry.
So K is also large?
So K is large from the point of view of being able to approximate P of psi of V, yes. So it's either the probability is smooth or K is large.
Okay.
Okay, and therefore what we can do is write the two terms together. So the first one was the energy of the derivative. The second one was this guy, and we can actually write the whole equation as one that depends on so this part depends on n squared, 1/n squared, and this one depends on the k squared. And we see that the total error somehow depends on the number of quantization level in the x-axis or the time axis, and the number of quantization level in the y-axis. And it's not a big surprise to see that the way that we relate between these two is 1 over the squared number of them. This is the squared error, and this is why it depends on the squared number of intervals in the x-axis and the squared number of elements that we have in the y-axis. Now, remember the game that we are playing to begin with. So I told you that your boss is giving you what is the opposite of boss? Your professor is giving you b number of bits, and now you have to distribute them into the n's and the k's. Now, the end of the case is a number of intervals that we are looking at. So how could we make it more? How should I say it? More rigorous. So the idea is going back to the basics. And by the way, these constants are given by the energy and in a sense also some sort of an energy. Okay. So this is the energy of the span of the values, and this is the energy of the derivative of the function. So the number of bits that you would have to distribute here would probably depend heavily on the smoothness of the function, and the number of bits that you would have to distribute here would depend heavily on how far phi L is from phi I. How large is this interval? Okay, and they compete obviously with one another. So so now we are engineers, we have to distribute bits. How do we do that? And the idea is quite, I wouldn't say simple, but almost simple. And the idea goes as follows. Remember that I told you that you have n log 2 of k bits that you can play with. So this is the number of bits that you can play with. And therefore, what we can do is write, I mean, if I'm looking at the number of bits that I'm giving k, I can say that this would be 2 to the power of b. Okay, so k could be defined as some 2 to the power of b, where b is the number of bits that I'm giving k. Okay, so basically b, the number of bits that I'm playing with would be n, would be the number of intervals, times k. Okay, times we already saw that the number of bits that I'm playing with would be n log k. Okay, so I can take k and plug 2 to the power of b instead of k, and therefore b would be nothing but n times b. So our problem of minimizing. Wait, I don't hear you very well. It says Mark, but I assume it's not Mark. So could you please
Oh, sorry, it was a mistake. Yeah. Sorry.
Okay. So what is going on here is that I have this minimization problem, and I know that I have this constraint that the number of bits that I am allowed to play with would be equal to b. Now, instead of k, I was putting the number of bits that I would need to represent k, which basically gave me n times b is equal to capital B. So if I would plug it in, what I'm getting is that instead of n squared, I could write b divided by b squared. Okay, so I plug it in, and instead of k squared, I could write 2b, which is k squared, which is basically this guy here. Now, I would like to have some notion of what is going on in a more compact way. What I can do is using the fact that e to the power of ln x is equal to x, and actually use this exponent instead of looking at the two. And here I have two functions. One of them is a function of b here, and the one of small b here, and the other one is a function of the small b here. Remember that capital B is a constant. It's a constant that somebody is giving us. So at the end of the day, what we see is that the definition of the error is giving to us as the following function. Okay, the following function. And if I would like to optimize with respect, so this is the error. Okay, so this is the MSE mean square error. And if I would like to optimize this error, what I need to do is take a derivative with respect to b and ask when is it equal to 0, and taking a quadratic term, the derivative of this quadratic term with respect to b would give me a linear term, okay? B squared derivative would be some linear function. And if I'm looking at this equation, it would give me an exponent as a power of b. So if I would put it all together as a graph, so again, remember that this guy, if now I would be looking at the following. So this would be b, and this would be my error, okay, or this function. So this would be my phi b, derivative of phi with respect to b. Okay, so this term would give me this linear function. This term would give me this kind of function. Okay, it's a logarithmic, sort of a logarithmic function with a minus sign. So this is why it would go down. Let me just see if I'm plotting it correctly. Just a second. I prepared it ahead of time, so why not using it? Yeah, so yeah, I probably did something right. So this is, so again, this is what is going on, and this point, the intersection point, is exactly the point where I'm getting this derivative equal to 0. So this would be the optimal b, and let's write b.
Isn't it the ascending function, the second one?
The second one is ascending, but remember that I have a minus sign here.
No, it's decreasing without the minus, so it's increasing with it.
I need to think about it. What, who is it? Omer or?
Me, Barak.
Barak. What Barak is saying is that this function should probably look like that.
Yeah.
Well, remember that here I have an inverse value with respect to b. Okay, so I think I am correct. I think that this is how it should look like. But check it out. I mean, at the end of the day, what I know is that I can plot. So I have some constant times exponent of some of another constant times b. Okay, with a minus sign. And obviously it should be lifted because I'm adding some constant. And this function should intersect that function, okay? And the intersection point is exactly where I can find my optimal b. So it doesn't really matter how you solve this equation, but once you solve it, you get the optimal way of distributing your capital B number of bits between the values of psi and the values that by which you quantize your time interval. Okay, so no, this is okay. Okay, so Barak, back to you. Remember that what I'm approximating is not this guy, but rather this guy. Okay, are you with me?
Yes.
So subtracting them from one another would give me these two functions. So thank you for raising this point. Please add the point, send Thomas the fact that you deserve a point here. So what Barak was saying, that look, if you look at this guy with the minus sign, then indeed it would look like something like that. Okay. But remember that we are asking when this function is equal to that function, okay? And when I write it like that, let me just remove the noise here. And when I write it like that, so this is the equation I'm trying to solve, what happens is that this function would look like that. And that function would look like that. And then everybody's happy. This is the optimal bit that I'm looking for. Okay, so this was a way of computing for the very specific case where we did a lot of assumptions along the way, and at the end of the day we got some equation by which we can distribute the bits. And if we don't have anything better to say about how to distribute the number of bits, then this is something that we can do. Now let's add more interesting assumptions to the game.
Question?
And see where it can lead us. Yeah, questions?
Yeah, I just was wondering why we started with the assumption that the capital B is capital N log K instead of just trying to minimize the amount of bits. Because isn't the whole point to minimize the amount of bits and not say I want exactly N log K and to see where I can distribute them?
Okay, so going backwards. So what Dan is asking is the following. Shouldn't we just minimize the number of bits? The answer is no. Somebody is giving me a budget, a capital B of bits. So this would be the number of bits that I'm allowed to distribute. Now the question is, how should I split these bits into the n's and the k's? Should n be a relatively large number, or should k be a relatively large number? And the answer is that if I'm looking at the number of possible vectors that I can represent by quantizing this guy to n and this guy to k, is 2 to the power, is k to the power of n. Okay, this is the number of different vectors that I can represent here. And then the question was, okay, so this number can be represented, as we said, as log 2. So this was log 2 of k times n. Okay, and this is obviously should be equal to b. Are you with me?
Yeah.
And now the question here was how to take b and split it into the k's and the n's. This is the optimization problem that I'm looking for. So the flow was like that. First of all, define the MSE. So the error or the MSE error is defined somehow. And at the end of the day, what you're getting is that in order to optimize your MSE, what you need to do is ask the following question: is ask where does these two functions collide? Okay, this would give you the optimal way of distributing b into the k's and the n's, and this b relates to k as k equals to 2 to the power of b, but it doesn't really matter. This is the optimal way of taking capital B number of bits and distributing them into the n's and the k's. Did I answer your question?
Yeah, I understand. Thank you.
Okay.
After I choose my optimal B and I choose let's say k points, how come k doesn't equal to n? If I have to choose several points of my function, the original function?
So the question that Oren asked is, how come the number of k's here is not equal to the number of n here? Well, I can think of various reasons. Let me give you an example. Assume that your function is really smooth, almost a constant, okay? And this would be your time. But it varies just a little bit here, okay? Then the question is, how would you like to represent, or let me go into even even to a more extreme case. Let's assume that your function looks like that. Here it is constant, and there is a jump. Here it's another constant, and there is a jump. Smooth jump, okay? It looks like that. Then what you would probably do is prefer to quantize n as fine as you can. You would like to distribute as many points as you like to n in order to capture these discontinuities, but it would be enough to give only one bit to your n's because it needs to represent only two values, okay? So in this So in this specific case, you would really like to give all your bits to n and very small number of bits to your sorry, this would be n to your k. Now you can think of a different example where you have this interesting function that is varying like that. And I mean, obviously, the more interesting the function is, the less level of the less number of bits you would like to assign to n and more to k. Okay, so this is where the competition comes into play, and this is when it becomes interesting. Okay, did I answer all the questions?
Yes, yes, thank you.
Thank you. Okay, so next, what happens next? How can I improve the construction that I've just did? So until now, we assume that the optimal estimator for phi at a given interval is given by the average, okay? So this is how, and this average is optimizing, we have seen it in the first lecture, is optimizing the integration over phi over psi minus my theta, and theta is my estimator. And we learned that the MSE error, if this is what I would be doing, would look like that. It would be the square of the energy. It would be the energy, the square of the signal, minus square the sum of the averages in each and every interval. Okay, so this is assuming that for each and every interval, I'm looking at my function and I'm allowing my quantization to pick a new, value that would be the average of this function in this interval, okay? So it's no longer quantizing the phi uniformly, but some oracle is telling me, look, in this interval, take the average of these values in the interval. So if for each interval we use the average of phi in this interval, then and again, assume that I'm giving a lot of n is relatively large, then I can build a probability for the values of phi along this axis. So again, if somebody would have given me this p of phi of v that we have talked about before, so how do I estimate this probability? And the way to estimate this probability is quantizing, for example, let's assume that I'm allowed to quantize my x-axis quite intensively. And then I'm measuring the value of each and every, quantized value of each and every interval separately. And then I accumulate them, if you think about it like a histogram. And from this histogram, remember that I have capital N values. And if this N is large enough, then I could have and assume that k is smaller than n, then I have this sort of probability function for the values of p, for the values of psi, of my function. Now, what I would like to do is find a k-level quantizer that optimizing this probability function. And this is something that we should already know how to do. Let's see.
In this case, we already chose the b bits, and we can decide between the k and the n because the k is decided by the n divisions. So
what we do is now saying, can we do better than the assumption of using, so the b bits that are distributed for the n's and for the k assumed uniform quantization here and uniform quantization there. I use the probability p phi in order to estimate the error, okay? Now assume that I would like to do a better way of distributing the points here, and I would like to give more values. I mean, I would like to, for example, assume that here I would like to do my quantization more finely, and here I would like to do my quantization less. Let's see if I can just delete this guy. And here I would like to have a coarse quantization level. Okay, how should I do that? If I would have known the probability, then it would have been great. I don't know the probability. So how do I estimate the probability of phi? What I'm telling you is that first of all, use this uniform quantization along the y-axis, accumulate, look at phi, the values of phi, accumulate them, and then you would see that there are a lot of phi's that are falling into this interval, and there are quite few phi's that are falling into this interval, okay? So this would be a way of estimating the probability of the probability or the density of the values of phi if I project them onto the y-axis. And I would like to use this knowledge in order to design better quantization, which would not be uniform. So it would not be a uniform quantization for the phi, but rather it would be some other quantization for phi. Okay, so I would like to get rid of this uniform quantization and get better, smaller quantization error, smaller estimation error. Okay, did I answer your question?
Yeah, I think so. Thank you.
Okay, so inside each and every interval, the error of estimating the estimation error looks like that. We've seen it in lecture 1. It would be the energy of the signal. So this would be integrating over the square of the interval times minus subtracting the square of the average in each and every interval. Okay, so it would be again, this would be the MSE error that we have seen I think in the first lecture. And the improvement for each and every interval, use the average for estimating phi. So again, assume that some oracle is giving that to us. I'm now talking on the previous. So the problem now is how do I estimate my P of psi, okay? And the idea is that if I know how to estimate my P of psi, what I would have with the new design, so if I have my P of phi, then with the new design, what I can do is find a new quantization. So I have a new way of quantizing the phi values. And with the new quantization, this is how the error would look like, where here, the only thing that we did is assume that I can estimate, that I can switch the average of the phi value, psi value at each and every interval by finding the average, okay? Average times the width of this interval. Okay, now if I add and subtract this term to the above equation, what I would get at the end of the day is that I have integration over the squared signal. Then I have to subtract the squared average at each and every interval. And here I'm getting something that looks like my quantization, my MSE for the quantization error, okay? For each and every interval. Now remember, all these intervals are the same, so I could push one, yeah, so these intervals are now uniform, so I can push 1 over n to the to here, and I can get rid of that. But this is how the MSE looks like. Okay, now these two terms I can write as sum. Now I can split this integral to integral over, remember that I have my intervals and each interval is delta I. So I can split the integral over from 0 to 1 to small integrals over each of these intervals. And this allows me to write the first two terms as follows. So I'm pulling the sum from the outside, the integral outside. And then within each interval, I'm subtracting from the energy, the squared, the summing, the squared of the signal minus the approximation of the signal at each and every interval. Okay. Now within each interval, what we can say is that the energy would be, sorry, so within each interval, what we have is that the energy is equal to that guy. And here, because the sum, sorry, because I have 1 over n here, I can just plug it outside, and then I have the squared signal here. Okay. So this is within each and every interval. Now I'm thinking aloud for a moment. Yeah, so if I multiply by 1 over sigma, these two would cancel. I mean, this one and this one would cancel. And this is obviously would give me the error within the interval, okay? So let's push it one more slide. So what do we have? We have that subtracting from the energy of the signal, this part, we get at the end of the day to the MSE of subtracting from phi the optimal guy that looks at the end as my regular MSE. I mean, subtracting from phi the optimal phi psi within each interval, which means that the square error is replacing is realized by replacing phi of t by the average in each interval. Okay, so when we are talking about the digitization, what we have seen is that if we have our function, and this is the 0 and the 1, and this would be my function, and I'm splitting it here into equal intervals, it would mean that first of all, I'm looking at each interval and I'm replacing the function by its average. So I'm looking at the average here, the average there, the average here. And if previously we assumed that we can choose this one, then now the average would not be the sampling of the signal at this specific point, but rather the average within each interval. Okay? And I'm looking at the p. Yep.
What is the approximation in the last step?
The approximation between here and here?
Yes.
I don't think that there is approximation. This is straightforward. Okay. This is the definition of the error in each interval.
Yeah.
Happens. Okay.
I think
So I'm looking at a constant, piecewise constant function. Again, point to Thomas. Thank you. So I'm looking at the piecewise constant function. And within each interval, what I'm looking for is the average in this function. Now, if this is what I would be by piecewise constant function, and this is the definition of this piecewise constant function, where in each and every interval I'm replacing the function with this average. So now the question that I would be asking is what would be the error of estimating my function with this average in each and every interval. Okay, so this is the first quantization that I will be doing. Okay. Afterwards, I will have to add the problem of not being able to use these averages, but rather restricting it further into some other way of approximating these values. But if I just leave it as is, then what happens is that I'm getting again the integration over the square of the signal. This is a constant that I cannot really get rid of, minus sum over these values, okay? Sum over these squared values. So if my signal, for example, would have been a piecewise constant to begin with, if by some luck this would have been my signal, then obviously my estimation error would have been 0, okay? And if my signal is is really, really sharp like that, then the averages would be the best, but I would probably get higher errors here, which are still optimal with respect to estimating each and every interval with a constant number. Okay. Okay, so when n is really, really, really large, then I can use the Taylor expansion about each point. Then and again, the times at which I'm sampling my, at which I'm the times are defined. The sampling times are the center of each and every interval. So these are the midpoints of each and every interval, and the psi I star is defined as basically the sampling the signal at the center. Again, this is for when n is really large, and therefore I can assume that phi is really smooth with respect of my sampling. Then within each and every sampling interval, I can assume my function to be almost linear, and therefore I can just sample the function in the central point. Okay, so if this is the case, again, so this would be my sampling point. If this is the case, then I can approximate the integration over the squared values of the signal. It would look like that, and at the end of the day, this is what I would be getting. So it would be the squared of the value of phi of psi in the interval plus the squared of the value of the derivative in the interval. And here I have the interval to the power of to the cubic power, and here I have the interval itself. Okay, so this is how the energy would look like, the integration over the square of the function inside this interval when I'm using a linear approximation for this function. Okay, and again, this is where n is really large, and thereby or therefore I can assume that psi is relatively smooth and doesn't change abruptly within the interval. Okay, so if this is my assumption, then let me just steal 2 more minutes. Then what we can do is we can have an approximation for this error where again, where we represent within each interval psi with the average in this interval. And we can basically write, instead of the first 2 terms, we can write the energy that we have now seen. And we have to subtract this guy from, because this is my, this is what I have to subtract when I'm looking for the MSE. Now you would immediately see that these 2 cancel out. And what we have is just the central term. I mean, just summing over something that looked like the Dirichlet energy, summing over the squared of the derivative of psi. Okay, over my interval. So this is indeed, and again, I can define this guy to be dt and move from summation into an integral, and this is indeed the Dirichlet energy of my signal. I mean, integrating over the energy of the derivative. And I have to multiply it by this constant, the number of quantization of intervals that I split my x-axis by squared, and then 1/12. Okay. Now for large n, what we say is that we can assume psi to be linear at each and every interval. So it means that I can approximate phi of psi as the average point, as the midpoint at each and every interval, which is the optimal psi star. I mean, this is the optimal psi for each and every interval. And for the second term, what we have, and for the second term, which is now taking these values and quantizing here, what I have is this error that I would analyze afterwards. Okay, so let's take, now it's 10:33. It's 10:33. Let's take until 10:53. Let's reconvene at 10:53. Okay, so now we take a break of about 20 minutes. It would allow you and me to break. If you have to drink something. If you have any questions, then please please ask.
2 slides ago,
Yeah.
isn't this the same approximation? Like you approximated the 1 over n to dt?
Slowly. Can you speak
2
slowly?
slides, yeah, in this slide where
Yeah.
you deleted the approximation, it's the approximation of 1 over n to dt.
I don't hear you. I'm sorry. In this slide, sorry.
Here, the approximation is from 1 over n to dt.
So what you're saying is that here the approximation goes from summing over these intervals into integration over dt.
Yeah.
Yeah. Okay. Maybe. I mean, I need to look back and see if how I define this guy. Let's go back and see.
Because the 1 over n just disappeared.
Yeah, you're absolutely right. So Omer, take back the 1 point that I.
It's me.
Oh, okay. No, so yeah, so Barak, okay. So this is how we define the MSE. Okay, and it's with summations and bringing it back. Okay, so it's here. So bringing, oh, sorry. Oh, I lost. So bringing it back here. Is probably shifting from the discrete sum over these guys. Okay, here I had the subtraction of phi t minus these approximations. So I just shifted into an integral here. Okay, good. So again, still the break would be until where did we stop? I think we stopped here, yeah?
Yeah.
Okay, so again, 10:53.
אמרת לי אולי חוץ מרן טיים צריך להתאים? וגם הדיפנדנטי. אין מישהו שהתקנו לו את זה כבר, שאני רק אעתיק לו את הספריות האלה משם? זה של מאיר, איך הם קוראים את הקהילה הזאת? יש איזה, מישהו כתב פעם איזה מסמך על זה, או מה? זה שאליהו הולך, אני שואל. אולי בלתי בשבילו בסדר. תגיד לי, אני שלחתי לך פעם משלוח מפתחות של הרקס שמשפיעים על זה. התחלתי משלוח במיילים לתעד. שלחתי לכם, לא רשמת את זה? בדרך כלל כל מה שאתה אומר להם, לא אחד. הוא שואל עודד ברון על כולם. שלחתי לכם כבר פעם. לא, מתי לא איתי. יש לך מספר? יש לך מספר שני? 881 רגע, אני לא בטוח. 88. אז תגיד לי את המספר. מה אמרת? 8813 241 בוקר טוב, אני מדבר. ברנאודה, התנצלתי. קודם כל תודה, לא, אני בעבודה.
Ron, can I ask you a question quickly?
Sure.
I was just wondering if we were to continue the expansion of the Tortelo, would we get a better approximation and like get third term and fourth term, or would that just not help us anymore?
Well, you will not be, remember that what we are doing here is analyzing our distribution of points. So if you would have more terms, then you would have difficulties doing the analysis. Saying that, obviously, the more terms that you add in your Taylor expansion, if you can carry on the analysis, would be better. So obviously, it would be better as long as your functions can be approximated by smooth functions. We'll see that some functions are smooth and therefore Taylor expansion would apply to them, and in some cases, Taylor expansion. I mean, if, for example, you have piecewise constants, constant functions, then Taylor expansion would do as good as just local and any other I mean, you don't have to go into higher order derivatives.
Yeah, because piecewise functions, you already have, I mean, somewhat of a signal, so it would be a little bit silly to look at it asymptotically.
Yep. So again, remember that our goal now here is to do the analysis, and it's not that I'm choosing Taylor as my favorite way of approximating. It would just give me an approximation that I can work with. So if, for example, in other cases, you can think of better way of approximating the signals, and we will see that. In some cases you can, then you can use that.
Okay, thank you.
Can I ask a quick question?
Sure.
So basically what we did before, we tried to like try not to just take the midpoint, but like the better option, like the average. And
Exactly.
after all the analysis, we got to the conclusion that just the midpoint is the optimum.
No. So there are two. So if the number of points, let me see if I can go that. If the number of points that you have is really large, if the number of endpoints that you have are really large, in which case you can assume that within each interval, the approximation of phi is linear, then taking the average or the midpoint would be the same. Okay?
Yeah, that's what I meant. I didn't say that, but that's what I meant, yeah.
Yeah. Now, if your intervals are larger and your function looks strangier, then taking the average, which we denoted as phi star, would be the optimal. Okay?
Okay, yes, thank you.
So, okay, so let's continue. What we are ready to do now is, in fact, look at the MSE that we have seen before. So let me just get rid of that. And remember that the MSE had two errors. One of them, this part, was the sampling in time. And that part was the quantization of psi. Okay, so quantization, so this one was the x-axis, roughly speaking, and this one was the y-axis, okay? We have seen that the first two terms can be written as such. So quantization in time, we did the analysis and we got something. And now we are ready to work with the quantization in the y-axis, in the values. So again, we had that digitizing in time gave us the following error at the end of the day. And now we are ready to work with the quantization of the values themselves. Okay. And we also said that when n is relatively large, then we can write the error as follows, as sum over the energy within each interval and sum over the derivative of square derivative of psi in these intervals. This is the thing that we have seen. And now, at the end of the day, what we got is that the MSE looked like that. Okay, so this was the first part. Now we are ready to deal with the second part. The second part is, now you may have, remember that we thought of a large number of these phi's. And now we cannot use these, I don't know, 5,000 numbers that we have here. We are allowed to use only 50 of them, okay? Not of them, just 50 numbers. How should we quantize? How should we split these values into other values that would minimize the MSE? So this part belongs to the quantization number. It has nothing to do, I mean, once you have decided on the number of n's and the number of k's, so it would obviously has little to do with the number of n's, but you do have to somehow cleverly choose the quantization level so that using first approximation, your value of psi and the quantized value of psi would be as small as possible, okay? So this is the part of the MSE that is being contributed by quantizing the psi values. And the question is, how should we do that, okay? So this is what we call the second term, or the third term if you go backwards. And now the question is, how can we play with it? So in the previous section, we showed that if we have the distribution of my psi's, if some oracle is giving me the distribution of the psi's, then the expected MSE, we have computed it to be as such, okay? So it would be, again, for a large quantization level K, okay? So really, really dense quantization level, assuming that the probability function is smooth. I mean, if you think about it, folding all the psi values onto the y-axis and accumulating them would give me the probability function or approximation of the probability function. And this is how the estimated error would look like. We've seen it in the previous slides. So this was true for relatively large n. And this was a way of approximating the quantization error. And now, if we are now allowing ourselves to look for an optimal quantization, we can plug it back into the MSE error. And what we get is that we have, so again, we have seen that the first part can be approximated as such, and the second part can be approximated as such, okay? And now if we recall our beta location problem, so we had to distribute our capital B bits into K's and N's. This was the approximation that we were looking for, but now we are allowed to distribute our K numbers so that it would also optimize for this one. So we are freeing the need from having K to be uniformly sampled here. We can distribute the psi intervals as something which is a little bit more optimal than uniform. Okay, so the question is, how can we distribute this K differently? Would be the issue, the next issue that we deal with. So let's do that. Let us write the following approximation for a function as being the multiplication of the quantization level by some constant value. What do I mean by that? Assume that this is my psi function, and I'm using a 1 on delta I function, which is the following function. It would be 1 inside the interval and 0 elsewhere. Okay, so this would be 1, and this would be my 1 delta I function. So this is delta I. I will use this function in order to represent my given signal as a piecewise constant function. So it would be psi 1 here, and then quantization of psi 2 here, etc., etc. Okay, and the way to represent this piecewise constant function is with this capital one or boldface one functions. Okay, so again, this is the definition of my one function. And then what we would like to prove is that among all possible constant, piecewise constant functions, what would be the best way of representing my functions? I mean, what should be my gamma 1 here, my gamma 2 here, etc., etc. And recall that we are allowed to use only k such gammas, okay? Yeah, somebody was asking a question. Isidias? Isidas? Guest? No? Somebody is, let me mute you. Okay. So the question is, how do we do that? And the answer, so let me go over that. And the answer is that remember how we define the energy, and let me just recall how we let's also define the distance between two signals so this is a definition of the distance is just integration over the square difference of the signals between 2 points, and we obviously have to take 1 over 2 at the end. I mean, we have to take the square root at the end. Pictorially, if my signal is defined between 0 and 1, so this would be psi 1, and there is also a psi 2, so there is also a psi 2, then what I'm basically taking is the sum of the square difference between these signals. Okay, so integrating over the square of this area, or the square of each and every difference between the psi 2 and the psi 1 would give me the distance between these two signals. Okay, so this is a way of defining distance between two signals. This is a way of measuring the size of a distance, the energy of a distance. Okay, so this would be the squared norm of a signal, and this would be the distance between two signals. So now we have a way of measuring discrepancy or distances between signals. Okay, so what we would like to do is project. I mean, project means that we are minimizing in some sense, in the sense that among all possible way of looking at it, we would like to project psi t into the space of piecewise constant signals. Okay, so this is what we will do. And piecewise constant, we write as PC at the top. Okay, this is what we will do. And the distance between the signals is nothing but our mean squared error. Okay, why? Because this is by definition the difference between my original signal and the piecewise constant approximation of the signal, which can be now the piecewise constant approximation can be written as my gamma 1 delta 1, and then gamma 2 1 delta 2, etc., etc. So this is how I approximate my piecewise constant signal. And at the end of the day, we can show that this is how the error would look like. And from the error, we can simply or trivially optimize for the gammas. And it should not come as a great surprise to see that the optimal gamma for each and every interval would be nothing but the
Average.
average. Thank you. So it would not be a surprise, a big surprise, that if you're looking at our signal and then we have our piecewise constant approximation, then this piecewise constant, this gamma I, should be nothing but the average of the signal in the interval delta I. And in fact, you can do it by taking the derivative of this term with respect to gamma I, and this is what you'd get. Okay, so this would be the result. So this should not come as a great surprise, but still we didn't. Now we have to quantize our gammas. I mean, somebody has to tell us you're not allowed to use as many gammas. In a general case, it would be n, capital N gammas, but it should be a much smaller value. It should be, I don't know, something which is smaller than capital N. So what we do next is we prove that the error of the signal represented by the optimal piecewise constant and then projected onto the general space of piecewise constant function is 0. What do I mean by that? It means that among all possible piecewise constant functions, the one that gets me the averages is the optimal one. Okay, how do we do that? Pictorially, if we think of our signal as some vector in a really high dimensional space, and assume that the space of all possible piecewise constant function is sitting here. Okay. What we will show is that when we project our signal psi of t onto the space of all piecewise constant functions, then the error, this is the error, is orthogonal to the space of piecewise constant functions, which means that there is no other piecewise constant function that would give me, it would better represent my signal, which is not a big surprise, but still, it is nice to show. So how do we do that? We use the inner product rules. So we have subtractions of two functions, and then we do the inner product with the piecewise constant function. So what happens here is that we can split it into two inner products. One of them is the inner product of the optimal piecewise constant with any piecewise constant, and the other one is the inner product of phi with any piecewise constant function. And now we write everything explicitly. And remember, these are piecewise constant at interval which are defined. Okay, so it's not any piecewise constant, but piecewise constant at intervals that are defined by my delta i's. So what we do is we write everything explicitly, and we have the first term as we see here, and we have the second term as we see over there. And if we do the math correctly, then what we get here is that we can pull the gamma I out of the sum and the sum out of the integration if we split the integration into these delta i's. And in the second part, we do the same. We can take the gamma is 1 over the gamma is already outside the integral. But what else we can do? We can take this guy out of the sum. I mean, out of the integration, and we can pull the integration inside and split it into deltas. And at the end of the day, what we get is that we are basically summing over exactly the same interval. I mean, sum over all the deltas of the 1i's would give me basically the whole domain. So this would give me nothing but 1. Okay. And then these two parts are basically the same. So at the end of the day, what we proved is that exactly what I showed you before, is that if I'm considering my signal as some vector in a very high dimensional space, and we project it onto the space of piecewise constant functions, or piecewise constant is at these intervals, then what we get is the best possible way. I mean, the error is something that cannot be projected and attains better error. Now, we are ready to do the next thing, and this is quantizing my gammas, okay? So now I have my gammas, my gamma values, which were optimized for and gave me the average within each and every interval. And now what I need to do is somehow quantize them. I mean, use only a finite set of numbers in order to represent them. And assume that my numbers are denoted as theta 1 to theta k, okay? It would introduce a new error to the game. So again, if k is somehow larger than n, then we are fine. But this would not be the case if you would optimize for b, because then we did something wrong. Okay, so k is probably smaller or much smaller than n, and then we are asking the following question: what would be my psi, my theta k's that would represent my gammas? Okay, so let's do the math and find which would be. And do you have any idea how to do that? I mean, how should I find the representative values for? So I have a set of gamma 1, until gamma n. And I would like to represent them as theta 1 to theta k. 2 points answer. How should I do that? Any ideas?
Maybe you find the two that are closest to each other, and then you represent them by their average or by some data point in the middle.
I will give you a hint.
can run maxoid on it, no?
Who was that?
Sean.
Sean, yeah. Max-Lloyd algorithm would be a solution. K-means, yeah, we just go to the previous lecture and this is how you would do that. I mean, it's a new problem. You have a set. So Sean, 2 points to tell Thomas. I don't know if it would be part of the homework or whatever, but it would be 2 points somewhere, okay? 2 points, nice to have. So yeah, we learned that if we have n numbers and we would like to represent them by smaller k, then the way to do that is to do Max-Lloyd K-means, I mean, call it whatever you like, but this would be the way. And indeed, this is what we'll probably do. I mean, we have a new problem to deal with, and we already know from the previous lecture that there is a way to do that, and this is what we will do. And now let's see what would be the contribution of this quantization error. Okay, so now we are looking at the contribution of the quantization error on the piecewise constant function that we already got. So we have our piecewise constant functions of gamma 1, gamma 2, etc., etc. And now we take these gammas and we change them a little bit. So it would not be here anymore, but it would be there. And this one would probably be there. And the next one would be probably here. And the question is, what would be these errors? I mean, what would be the subtraction of each and every, I mean, now I'm looking for the area that I'm introducing by representing my piecewise constant function by quantizing the values of this function. So we plug, I mean, we write the piecewise constant function explicitly and the quantization quantized version explicitly. And what we see is that we need at each and every interval to simply subtract one number from the other, okay? And if we do that, then what we end up having is summing over the quantization levels at each and every interval times 1, okay? Just get rid of that. That's it, times 1. For some reason, even when my telephone is on mute, I'm getting the telephones, I'm getting the phone calls. So at the end of the day,
are we so assuming that the
just a second. Yeah, sorry.
Are we assuming that the intervals on the x-axis are matching to the intervals on the y-axis?
So we are assuming that somebody gave us the split on the x-axis, okay? And now we are just dealing with the following problem. Somebody is giving me the piecewise constant best approximation of my signal, okay? So in order to represent it, I need n gammas. And now he or she is telling me, look, you cannot have these n numbers. You can use only a small number of k in order to represent them. So you cannot represent it as such. You would have to represent all of these as the same number. And all of these as the same number. So now it looks like a really noisy image. And we'll have to denoise it. So yes, all events are happening at exactly the same location. So it would be all set of functions that are piecewise constant at these locations, okay? So these are the locations where the events are happening. It wouldn't happen anywhere. Barak, did I answer your question?
Yes, thank you.
Okay. So this is what we would be doing. And in fact, what is happening is that what we have is the following summation. Okay, so each and every interval is contributing the the difference between the two values times the interval of the corresponding delta. Okay, and we can just put it out of the summation. Since we are sampling uniformly, it would just be 1/n, and this would be my optimization criteria. Okay, so we are looking for the optimal quantization for gamma I for the nearest theta equals 1 to k. And the question then is how to do that. And Sean already said that what you need to do is probably do something like our good old k-means or max Lloyd that we did before. Now what we see is the following. We have here two sources of errors. One of them is the projecting onto the piecewise constant values, and the other one is projecting onto the space of all piecewise constant functions. Okay, so if I plot it like that, I'll just get rid of the blue here. So if I just plot my psi of t as this general function, what I can do is look at the space of all possible. So this is the space of all possible piecewise constant functions. Okay, so first of all, I would project it onto the space of all possible piecewise constant functions, and I would get something here. And if I would have, for example, and the set, okay, so this is the space of all piecewise constant functions, and now I also need to plot in this space the space of all piecewise quantized. So let me write PC quantized, or let's do it like that. Piecewise constant with a q here, and this would be my other points. It would be, let's assume that one, that one, that one, that one, and that one. So initially, what I'm showing you is that projecting this psi onto this, so it would not, sorry. So projecting this psi onto the space of all possible piecewise constant would be this guy, and then projecting it onto the nearest neighbor, which is piecewise constant quantized, would be this one. And there would be no other way. So there is 90 degrees here and 90 degrees there. There is no other way of getting more optimal, a better way of representing psi. I mean, in many senses, projecting into the space of piecewise constants is one way, and then what I have to do is also add the quantization, which is projecting the piecewise constant onto the quantization levels. So the two errors are actually forming, if you think about it, a Euclidean space. One of them is being the result of the sampling along the t or the x-axis, and the other one is being contributed by quantizing along the y-axis. Okay, along these values. And this is a nice way of looking at it. I mean, you can split the problem, roughly saying, into two. And now the question is, how do we continue from here? And to that end, what we do is jump immediately to the next chapter, to chapter 4. Oh, and for that I need to LaTeX again my text. Sorry for that, for compiling online. Oops. Okay. And my hope is that it would immediately show up here. Yep. This is the magic of Okay, so now we are ready for chapter 1. So just to remind you what we have been doing, let's see if I can enlarge it a little bit more. What we have been doing is the following. We have been, so what are we doing right now? Until now, what we did is we got a function, okay? And we said that if this is my function, I need to sample it in the x-axis and in the y-axis. And this is how I would represent my, my function with a finite set of numbers, okay? So I'm having a vector and the entries of these vectors are quantized, and I did all the math in order to show you that quantization along the x-axis and the y-axis can be split into two different problems, and you can analyze them, and everybody should have been really, really happy with that. Now, the next question that we would like to also ask ourselves is, can I have a better way of looking at these kind of functions? And
before we continue, could you share these slides so we can take notes on them?
how do I do that? I can send.
I mean, like the previous lectures, only the first three are available in the website.
You sound really aliased, so I don't understand what you say. But what I can.
It's not on the website. The chapter 4.
In the website, let me try to send you the file. So I will allow access. I would now allow access to my lectures. Let's see. Not lectures, sorry. So it would take 1 second. Let's see how I do that. Yep. So it would now take about half an hour to upload it to Zoom, and then you should be able to access it from Zoom if it's okay with you. Okay, so it's on the way. It's about halfway there, and the idea goes as follows. So if before what we had is this kind of a function, now what we would like to do is ask the question: can I find a family of functions by which I can represent my given function? So, so until now, again, what we saw is that, you got it in the chat?
Yes.
Yes.
Okay. So what we had until now is that we had our function psi, we quantized it, and we said that we are now, in a sense, projecting it into the set of all vectors, and we had k to the power of n such vectors, okay, so different vectors. If we quantize the x-axis by n and the y-axis by k. Okay, but the question is, if we have now this kind of number of different functions to deal with, and assume that I don't want to represent my functions only as piecewise constant functions, what should I do? So getting into the continuum is something that we will do later on in this course, but let's limit ourselves for the time being with the following. So we had some way of digitizing my functions, and we call it capital D, and then quantizing the functions using some quantization function that we denoted as Q. And thus we replace the continuous function with a piecewise constant function. This was Q, and these were my 1 functions that were getting 1 along the interval delta I and 0 elsewhere. Okay, so this was a way of projecting my functions into the set of piecewise constant functions, where piecewise constants were not at arbitrary location, but rather at very specific locations. At these locations that are happening only every delta I or 1/n locations. Okay, we can represent our functions with a different set of numbers that would lead to a smaller MSE error. And for the time being, we'll use our 1 in order to represent in order to analyze our errors. Okay, so again, remember this is our I. And the question is, can we represent the functions with a different set of numbers? So let's see what is going on here. Now, instead of choosing n numbers, let's choose n functions. Okay. So now assume that my functions all look like that. Okay, they all look like that. One of them looks like that, another one looks like that, etc., etc. So it appears that if I take something that looks like a sine wave or a sine function, and all I do is amplify its value, then with a single function and then another number, I can probably represent my functions. Okay. So now I'm allowed to use n functions. Each one is a mapping from 0, 1 to the real numbers or the complex number for that matters. And the other thing is that I would like my functions to be a basis. Why? In more advanced courses, you will see that this is not a restriction. And in fact, when you lose this restriction, you can do magic. But for the time being, from some sort of looking at what I can do optimally, assume that I have a basis. And in a basis, I can represent points in a very efficient way. I can just project it onto my basis and then get the coordinates of these points and thereby represent my points in this high dimensional space. So the moment I'm saying that the family is orthonormal, okay, orthonormal means that the inner product, and this is how I define the inner product, would be equal to delta ij, where this is the Kronecker delta, which means that if the two functions are the same, it would give me 1, and if the two functions are different, it would give me 0. If,
Can
for
I ask a
example,
question?
Yeah.
How could n functions create a basis? Like, isn't I guess that the vector space of functions is sort of infinite, so it's weird. Even if they're orthonormal, how could they span the entire space of functions?
I didn't say that they span the entire space of functions.
But
Excellent question.
Doesn't that what a basis means?
Okay. Okay. So what again is saying, look, if you're looking at the space of all possible functions, then the fact that you're giving me an n functions would never span the infinite dimensional space of all functions. Obviously, you're absolutely right. When I would talk about a basis, I would have to limit my set of possible functions to all functions that can be represented with this kind of orthonormal basis. And then I would be able to talk about it as a basis. But later on in this course, what we will see is that even when we talk about all possible functions, and for that matters, let's assume all possible functions for which I can assume that the derivative is somehow bounded, okay? So assume that I'm looking for all these functions, okay? And then the question that we will ask is, what would be the best basis by which I can represent these kind of functions that would give me the smallest error in some sense, either MSE or something else, okay? So again, the basis for all possible functions for the infinite dimensional set of functions whose energy or Dirichlet energy is smaller than 1 is obviously infinite. But now assume that in some sense, I would like to truncate this infinite dimensional basis and look at only the first leading n vectors, exactly like we did in the quantization. And the question is, how should we do that? So first of all, just to give you intuition about such functions, let's think of the following function. Let's assume that I have a sine function. So this would be 0, and this would be 2 pi. And this would be sine of x, okay? And this would be x. Can you think, or t? Okay, this would be t. Can you think of another function that would be orthogonal to this one? Anyone?
1.
Again?
The constant 1.
Yeah, the constant 1. So what Barak is saying, that the constant 1 would obviously be orthogonal to them. Why? Because if you sum over this guy and that guy, you'd get 0. Another function?
Cosine.
Yeah, so the cosine, if I'm looking at the cosine, okay, Barak, you're accumulating too many points. Another point too. So the cosine should also be 1, that when I integrate the cosine with respect to the sine, I would get 0 at the end. I mean, check it out. The cosine is an antisymmetric function. The sine is a symmetric function. If I integrate it over the interval 0 to 2 pi, what I would get is 0. Okay, and there are obviously infinite number of functions like that. So you can find functions like that. Let me give you a trivial example. If, for example, I'm taking my 1 functions, okay, so this would be the first function, the second function would be this one, the next one would be this one. So if I normalize them properly, so it's such that the area here is 1, then these functions would be orthonormal to one another, and they would also span, I mean, they would also be a basis for what?
For the piecewise constant space.
Yeah, thank you. So there would be a basis for the piecewise constant functions. Did I tell you to tell Tom that you have an extra point? So if I didn't, then now I do. So now what we need to do is look at our signal, and our signal could be a projection, I mean, some linear combination of these set of n numbers. And how do I write this linear combination? There are scalars that should multiply each and every of these betas. And these scalars are define the approximation of psi by the beta functions. And we write it psi with a small beta at the top, okay? So this is my approximation of psi by projecting, I mean, we didn't say project yet, but in a moment we will show that projecting it onto this orthonormal family is the right way to go. But this would be a way of representing psi by a linear combination of the beta functions, okay? And these coefficients, these set of scalars are optimized for example, if we measure the MSE of subtracting the approximated function from the original one. So what we'll do is optimize for the L2 errors of the mean squared error. And if we do that, let's do that. If we do that, let me jump to the conclusion and then show you how we do that. If we do that, then surprise, surprise, what we get is that the thing that we have to do is project our function onto the corresponding, not basis, but rather elements of my family, functions of my family, okay? So the optimal coefficient of representing psi in the beta space would be projecting psi into beta I. So this would be the coefficient, this would be the scalar coefficient psi I. Now, how do we get there? What we do is we measure the MSE, which is nothing but what you see here at the top. And now we can, since we know how this psi beta is defined, we write it explicitly. If we write it explicitly, we can open the brackets and then get these two terms over here. We can pull all the sums out of the integration and switch the order of the integration so that the sums are outside and the integration is inside. And at the end of the day, what we get is the following term that we have to take, that we have to differentiate with respect. So now what we do is we take the derivative with respect to beta I, to what? To psi of beta I. Okay, so we take the derivative with respect to these guys. And what we get is that if we take the derivative and equate it to 0, at the end of the day, what we obtain is exactly what we suspected, that indeed, in order to get the best way, the best scalars is to take our function, and now I'm plotting this function as point in this infinite dimensional space, and then resort to our betas, which are, each of them can be thought of as a vector, and they are orthogonal to one another. Okay, which means that if I project one to the other, and then all I do is project my function onto these betas, and I get my coordinate. Okay, so these all would be 90 degrees, and what I get is my coordinates, which are my psi beta I. So this would be beta I. Okay, so if we would have had the luxury of having a set of functions beta i's, n of them, and if we would like to represent our psi functions as belonging as a linear combinations of these betas, then the optimal way to do that would be to project our function onto this orthogonal set of onto this family. What would be the error then? The error is something which is easy to compute. I mean, this would be the MSE error. It would be integrating over the I mean, we have already seen that it would be integrating over the energy of the signal minus the inner product of the signal projected onto the betas, and obviously you have to square it, okay? And we already know that this one is denoted as, I mean, the projectant is nothing but these colors. So it's basically subtracting from the energy of the signal the energy of its coefficients, when projecting it onto the beta i's. Okay, now what happens if on top of that we also have to quantize these numbers? So assume that you no longer allowed to have any possible number, but you introduce a new source of error, which would be the quantization of these numbers. So again, as we did before, we probably go back to the Max-Lloyd k-means and we do the quantization. And now the new signal, which would be a little bit further away from my, so if I've taken my signal beta, my signal psi, and projected it onto the subspace of betas and got this one, so now projecting it further into the space of all possible quantized, I introduce a new error, okay? So again, there is 90 degrees here, and there should also probably be 90 degrees here, and this would be my quantized version of the signal, of the coefficients of the signal. So this would be my my reconstructed signal. So it would be quantizing the values of the coefficients of the betas, and the error would be subtracting. The definition of the error would be subtracting from the original signal the now quantized and projected vector. Okay, so this is how it is defined. Let's try to estimate it. I mean, let's, yeah, questions?
In what sense is there 90 degrees on the quantized?
In a moment we'll see. In a moment we'll see. When I'm saying that, I'm saying that the if I'm looking at the error, it should be equal to the projection error squared plus the quantization error squared. Okay, so the Euclidean way of looking at things should be like that. So in this sense, it would be 90 degrees. So it would mean that there would be no other candidate in the space of quantized values that would give you a better error. You would like to have your quantization error optimally defined. And if you do that, you can basically split between the projection and the quantization. Okay, in that sense, we'll have these 90 degrees. So let's prove that what I'm saying here is not nonsense. So how would we define the MSE error? So now instead of just looking at the coefficients as we did before, now what we do is introduce here the quantized coefficients. And again, we open the parentheses and we have here these 2's, and we have here the squared of the coefficients, because remember that when we integrate over betas, we get, I mean, the integration of a beta I dt is equal to 1. Okay, so the energy of beta is equal to 1. And then what we have here are the
Beta I squared.
Sorry?
Beta I squared.
Yeah, thank you. Beta I squared is equal to 1. So, and here what I'm getting is indeed integration of a beta I squared. So what we have here are the coefficients, are the psi beta i's. Okay, these are these guys. What we have here is sum over the quantized levels. And what we have here, the first part, is nothing but the original projection error. Okay, so what I told you is indeed correct. What I have here is squared the error of projecting onto the beta space plus squaring the error of quantizing. Okay, so indeed, and this is how the quantization error is being defined. So indeed, when I do my quantization, if I do it properly, then what I'm getting is that I have that the total error, the sum of the squared error, is equal to the square of the projection onto the betas, and then the error that is being contributed by the quantization. Okay, and this is a really nice property, because if they are unrelated, we can probably optimize each of them separately. I mean, obviously, first have to optimize with respect to the first, and then with respect to the second. And what should have been plotted here is the fact is exactly what I did before. Let me try to do it like that. So this would have been my signal. Here, replace colors. So this would have been my psi. Sorry. So this would have been my psi of t. Then here should have been my betas. So this would have been my beta domain, and I'm projecting it onto the beta domains. So this is projecting onto the beta domains. And here within the beta domains, I also have my quantization domain, and the quantization is, say, a sparse set of points here, and projecting onto the beta domains, it would also be a 90 degrees. Okay, so what I've done here is optimize for the projection onto the betas, and then projecting onto the so this would be the value of the quantization. Okay. Okay, so this is it, and now we are ready to push forward. So somebody is giving me a family of orthonormal functions.
Well,
yep.
why did we switch from orthogonal to orthonormal?
Orthogonal usually means basis, and when we are dealing with infinite dimensional space, we cannot call it a basis. As who was that defined it before? Who was the guy that mentioned it before? Yagel, yeah. So Yagel Meir said before that you cannot say orthogonal because then it defines a basis. So these are orthonormal. So if we just look at the subspace spanned by this n function, we can relate to it as orthogonal. But now they would be orthonormal. Where the mapping of each and every of these bi's is into the real or the complex. And we used it in order to represent our psi function. And we showed that the best way in a least square sense to represent my function would be with the scalar coefficients that multiply my betas. And the way to achieve these scalar coefficients is nothing but projecting this psi into this orthonormal space. So saying orthonormal basis would be saying like orthogonal. I would not say basis because I don't want to claim that that I can span the full space of all possible smooth functions or even not smooth functions. Okay. So let's now write the approximation as follows. Okay, so I'm writing the approximation by now. Okay, so let me recap. So orthonormal is orthogonal plus normalized. Okay, thank you. So who is that? Tom. Thank you. So it's always good to have a mathematician here. So orthogonal means that the norm of these betas is not necessarily 1. And when I say orthonormal, I mean that I do force it to be 1. Okay? Okay, but I'm not saying a basis. Tom, am I correct?
Okay, so a basis is just relating to the span. So it's a family. Basis would be everyone can be represented exactly with that family. So orthonormal is independent of the property of basis. Basis just means that everything lives in this space. If it's just a family, then there are other functions or vectors that can live outside the span of this set of things you're working with.
So again, saying it in exactly the same words that I did before, it means that this one is not representing the space of all possible smooth functions, and therefore I don't relate to it as a basis. But it is a basis of the span of whatever they can represent. So if I'm living just in the space of these n functions, I can in fact talk about the basis. Now assume that somebody is telling me, look, you have indeed n numbers that you can play with, and capital N numbers. But now I'm allowing you to use only a small number of them, much smaller than n. So if n, capital N is 1,000, assume that I'm allowing you to use only 10 of them. What should I do then? I mean, what should be the way that I'm selecting these n numbers? In order to do that, what I do is now relate to an approximation of psi as being a way of choosing only n of these numbers. Okay, so now I'm projecting my psi on only the first beta i's that that define my orthonormal functions. Okay, so I'm truncating it here at n, which is smaller than capital N. Okay, so what would happen to the discretization? And we call it discretization error. And obviously, the more n we have, the larger n, the smaller the discretization error would be. So in this specific case, we can order the betas in order to somehow define how my error behaves. And let me give you an example where this one is really, really, really important. I don't know if you are familiar with the way that you are now compressing your images, but usually your images are being compressed with a way of working with JPEG, okay? And in JPEG, what you do is you look at patches of a certain size, and you project them into something which is called a cosine transform, but it doesn't really matter. And then you pick only the first, I would say, 20 to 40 coefficients. Okay, so what you need to do is to order your betas, your cosine transforms, in a way that would allow you to pick only the first 20 or 40. It depends how much you compress. I mean, it goes between 10 to 40 in a way that would allow you to get the best way of how your patch look like in the image. Okay, so it would be really important to order these betas in a way that would allow you to account for the more important observations of your data. I mean, it would have to somehow relate to how your psi's look like, so that you would be able to represent them properly. So if we look at the error, and here what we do is actually look at the error, then it would be the energy of the signal, which is obviously something that we cannot really play with, minus the projection of the signal to the first betas that I'm using. Okay. So obviously the order of beta determines how the error behaves. So what do you think? How should we choose our beta? Assuming that I have a single signal, okay, one given signal. So how should I choose my my betas in order to best represent my signal? Assuming that I can choose only a small number of n's here. Any ideas?
Maybe we can choose the largest projection.
Yeah, so what Michael is suggesting is first of all picking the largest projection, and then the second largest, and then the second largest. And this is how I should probably order my betas. And this would be the fundamental idea behind what we will do in the next lectures in this course, is how to order my betas so that the projection, the initial projections onto my betas would be as good as possible in the sense of representing my signals. So how would the MSE error look like? Remember that what we would like to do is reduce the MSE error in the most efficient way, okay? And the way to do that, now let me go into the slide that I've already prepared at home. Forget about it. So what we would like is for the MSE to decrease as efficiently as possible. And what we will do is we'll choose the first beta to be the one that maximizes the projection onto the beta. So yeah, we will call it beta, psi of beta first, okay? And then we'll choose the next projection and the next projection and the next projection. And if we plot the error, okay, so obviously when I'm taking my n to be capital N, I would go into let's plot this error. And remember that this error is decreasing as a function of this projection. Why? Because the beta, the norm of the beta is 1. So what happens is that first of all, assuming this is the energy of my signal. Okay, so this would be phi squared. Okay, I'm projecting it onto nothing. So this would just be the energy of the signal. Picking up the first one, and this is picking up beta 1, beta 2, etc., etc. And in beta k, or beta, this would be beta n, the error is something which is bounded. I cannot go below this error. What I would like to do is that the first error would be as small as possible. So this would be the largest possible projection that I'm looking for. Then the second projection would be the largest of all possible projections. So this would be the second one. The third one will probably be here. And at the end of the day, if I will look at this graph, it would be a monotonically decreasing graph, but the slope would always decrease as we go to the right. Why? Because we are picking up the values, the residual of the values that we are still, that would still allow us to represent our signal the best possible way. So again, this is n, and this is the right way of choosing my coefficients by which I represent my signal. Okay. So,
but if you are choosing different functions to different basis functions to different functions, then you need to represent also the index of the basis number. You need to add it to the representation, right?
So just to translate what you're saying into what I think you're saying that if now I'm choosing not beta, but rather a new set of functions gammas, then you'll have to translate these numbers into this new basis. Was that correct?
I said that if you're changing the order of the betas for every function, then you need to add it to the representation.
Well, until now, what I did is treated only a single psi function. And what Barak is saying is correct. If tomorrow I would have a new function, a new psi of t, so it would be new. Let's call it I don't know, not psi, but rather psi of t. Okay. So now I would like to represent psi of t with my betas. Then obviously the order of betas should be different, because choosing the largest number would probably have a different order compared to my original one. Then obviously you're right, I would have to reorder my betas. And at the end of the day, what we will do is we'll look at the statistics of psi and then order my betas so that they would fit in the best statistical possible way to the appearance of my psi's. So I cannot do it assume that I cannot reorder my betas for any psi. So what I will do is reorder them for the statistics of the family. But until we do that, let's focus on a single psi and single betas and just order them. to work with me. So again, the error should decrease, and obviously, if I'm choosing my function correctly, and they're orthogonal to one another, I would like that as n goes to infinity, the error should also go to 0. Okay. Okay. Now, so these are the numbers that we have to quantize. Okay, these are the numbers that after projecting psi's into the betas, we have to quantize. And now what we'll do is use the Cauchy-Schwarz inequality in order to show that the energy of this projection is smaller than the maximum between the two absolute values of my function. And remember, why do I need both of them? Because I can look at my function and it could have a negative value here. So the absolute value of psi low could be actually higher than the absolute value of psi high. Let me go backwards a little bit. Okay. So if we use the Cauchy-Schwarz inequality, what we have here is that projecting psi onto the betas is equal to the energy of psi. I mean, this integrating over the square of psi, and integrating over the square of each of beta I, and we know already that this one is equal to 1. Okay. So what we have is that the projection of psi into beta I is equal to nothing but the norm of the energy. I mean, taking the square root over the integration over the square of psi. And since this is true, we know that it would have been smaller than it, assuming that my function is getting its extremum value either here or there, it would obviously be smaller or equal than integrating over between 0 and 1 over this value. Okay. So obviously, the energy of my signal would have been smaller than this area if psi low is smaller, is larger in absolute value than psi high. Okay. Okay. Now, what we also know is that I can bound this projection between minus this value and plus this value. Okay, so remember that what I'm doing is, the only thing that I'm doing is saying that projecting psi into the betas is bounded from above and below by the low or high value of the function. That's it. Now what we'll do is add uniform quantization to my betas. So now I'm taking this, we call it psi beta i's, something like that, or beta i's. And what we do is we quantize them. Now, we have already seen that it would be smaller than the projection, than the square projection of psi over the betas. So what we can immediately write is that it would be, so we know that it would be smaller than n divided, I mean, if we sum over n, it would be n divided by 12. And 1 over k squared. I mean, this is what we have seen before. But here I can plug, instead of this term, okay, I can immediately plug the max of these values. I mean, I can use the Cauchy-Schwarz inequality to come up with the final solution that would read as follows. So it would be so it would look like that. Okay, so again, using the Cauchy-Schwarz inequality, we can show that the error of projecting my psi onto betas and then quantizing is smaller than this part. Okay, and we use our equation from before that allows us to quantify the quantization error when projecting into n numbers. Into k numbers. Okay. Now putting everything together. Oh, I'm running out of time. So let's Let me see how complicated it would be. Let me just continue for 2 more slides and then. So what I'm saying here is that the quantization error is independent of the order of beta i's, okay? And there is no solution for the optimal beta location, but what I can do is write the MSE of quantizing into k intervals and n functions that would at the end of the day look as follows, okay? It would look as the maximum squared of the value of psi, and I have this coefficient here, and here I have the MSE error of projecting my function onto the beta family, okay? So remember, beforehand, what we had is that defining the total number of bits as n log 2 of k, and we denoted k to be 2 to the power of b, and therefore we could plug b to be b total divided by n, and when we plug everything in, what we get at the end of the day is that the MSE error as a function of n and capital B looks as follows. Okay, it reads as follows. And what we see is that we have we have this dependency and that dependency and that dependency on n. So this is something that we can plot. I mean, this is a function that we could plot, and this is yet another function that we could plot. And in fact, what we have, let me just plot these 2 numbers and see where we go. What we have is something like that. So this is the beta location problem, and what we have here, let me do it with something that looks a little bit clearer. So what we have here, the x-axis would be my number of bits that I'm assigning, that I'm using. I mean, it would not be the number of bits, but rather it would be, it would infer to k, which would be 2 to the power of b divided by n. Okay, so this would be my n. So n would be this axis. And what I'm seeing here is that if I would look at the previous equation, I have one equation that is the MSE error as a function of n, and this is a function that we've seen goes like that. Okay, and there is another function which is the a some constant times n divided by another constant to the power of 1 over n. This was the second term, and this function goes like that, probably. And if I add these 2 functions, I will get a function that looks like that. So this would be the overall function that I'm looking at. And the minimum point of this function is here. I mean, this is something that I can explore and investigate. So this would be the optimal n, the optimal number of functions that I would be using if the total number of bits and then quantization of these numbers is a fixed number, which is equal to b total. Okay. So what we do here is allocating bi number of bits to each coefficient. So as the total number of bits is equal to b total. Okay, so exactly like we did before, but now the error function is a little bit more complicated. We could investigate this function and at the end of the day come up with a solution that would tell us how to distribute our bits between the number of functions that we are looking at and how we quantize these numbers and how we actually apply the quantization operator to these numbers. Okay, so this is enough for today. I think I even stretched it a little bit, and if you have any questions, this is the time to raise them up. And I see that Tom also gave you some other hints about what is the definition of these betas. and what is the definition of a span, and what is the relation between an orthonormal, orthogonal, family, and the basis. More questions? If not, then thank you for today, and we'll meet next week.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks and bye.
Thank you.